Past slide here.
Yes, sir.
Good afternoon to all IEM and UEM family members. And today, as you can see, sparse identification of nonlinear dynamical systems from data. Okay, too many buzzwords and keywords, I believe, but I'm sure Professor Prabrit Bandyopadhyay, Department of Electrical Engineering, University of Engineering and Management, Jaipur, will make all those keywords simple for all of us. And definitely, I'm sure that you are going to present it in a way treating that each one of us belong to different departments and not from your department. So I'm sure you will make it easy for all of us. So interested to listen to it. Thank you, Professor Prabrit. You may take over from here.
Good afternoon, sir, our Honorable Vice Chancellor, sir, and good afternoon to all my senior colleagues present here. Thank you for providing me with such a good opportunity to showcase some of the works that is happening in the field of engineering and as well as science. So today I am going to discuss one of such topic which says sparse identification of, just a second. Yeah, sparse identification of nonlinear dynamical systems from data. So as our Vice Chancellor sir pointed over here, there are a lot of big words over here. So let's try to demodulate each one simultaneously. So first of all, let's try to understand what is a dynamical system. So as you all know, a dynamical system is a system which changes with time. Time has a reflection on these sort of systems. For example, any system around us, any real life systems, even us, we human beings, are dynamical systems. For example, you have bought a car like 4 or 5 years back. The time when you bought the car, it was in a full-fledged, like very good shape. But with time, the performance, the other features of the car gets reduced. So that is the effect of time on dynamical systems. A dynamical system never remain constant with time. With time, they have some sort of change, and that's what makes them really interesting. So first of all, how we have tried to understand or try to manipulate these systems, it was a very simple approach. First of all, from the very early ages of our science, what our scholars tried to do was, first of all, they tried to understand the system from a mathematical perspective. What is a mathematical perspective? A mathematical perspective is nothing but when you can understand a system by actual physical laws governing those things is the approach that conventionally we used to follow. So for example, if we take a simple example of a pendulum or an inverted pendulum, what do? We simply write down the equation that according to us reflects the dynamics of that particular pendulum. Or in case of inverted pendulum, we do the same. And as we know, these systems are non-linear, inherently non-linear. By the way, what is a non-linear system? A system which does not abides by the law of superposition is a non-linear system. Okay, so what we used to do is, first of all, we tried to make a formulation of these non-linear systems using mathematical equivalents, mathematical laws. And from those mathematical laws, what we used to do, we used to try to linearize the system around particular points. And after that, once we are done with this linearization, by our conventional linear control system tools or linear system analysis tools, which are very, very powerful, we used to analyze those kind of systems. Now, from these kind of ideas, control system was first introduced, or it came to the understanding of people. But with time, what happened is the complexity of the problems, or rather of the systems, increased, which added huge amount of problems in these sort of an approach. So before going to that, let's first try to understand what is a control system, a very basic approach. So according to from a very theoretical perspective, it's nothing but it's an optimization of systems that's contained by the laws of physics. For example, you are driving a bicycle by a road. Okay, so now a bicycle has various input and output parameters. For example, the pedal that you are by which you are applying the forces, it's an input. The brake of the bicycle, it's also an input. So depending on your necessity, depending on the necessity of your speed, the position of the bicycle, you apply various types of controls, inputs, whatever you want to say, and based on that you control the system. So what you are basically doing is, the bicycle is governed by basic laws of physics, the three laws of Newton's dynamics, but there are spaces between these things where you can optimize these laws. What exactly I'm trying to say is, for example, if you are driving a bicycle in a straight road, you have to constantly keep on pedaling the bicycle so that you can get a forward motion, right? But whenever you are riding this bicycle down a hilly road, back of the mind, your brain understands that from your day-to-day experiences, that this bicycle, when it's going down through a hilly road, it does not need a constant pedal or a constant input. Rather, if you are doing constant pedaling when you are driving down a hilly road, it's actually quite dangerous, because it may create a speed, create a speed which is very much dangerous for the stability of the bicycle. So that's why, based on our experiences, we manipulate the systems, we optimize the systems. And this whole idea of manipulating or optimizing a systems that is constrained by the physical laws or laws of nature, this is the basic ideology behind this subject called control systems. Now, as you can see in this basic diagram, a control system has very few basic components. First, there is something called a state vector. Here you can see it's written like x dot equal to fxu. So this x represents the state vectors. There is another component called the input. Input is this u represent the input. Output, here y represents the output, and as you can see, the sensor and actuators are also present in the system. For example, the sensors sense the system input or output, and depending on the value that has been sensed by the sensor, the actuator takes control. If the system needs some kind of input or some kind of optimization, or rather some kind of you need to change some sort of variables, some sort of parameters, that's what we do by the use of actuators. Okay, and finally, a controller is nothing but, a controller is the idea by which a system is governed depending on its output. So if you have to write down the equation for the controller over here, you will write something that is varied with y. So the controller is depending on the system's measurements or outputs. Okay, so these are the very basic components of a conventional control system. And simultaneously, there are another two things present in systems. First of all, there is something called disturbances. So an ideal control system is it's supposed to have no disturbances at all. But in real life cases, as you can understand, there are a lot of disturbances that happen in any system whenever you try to achieve a goal. For example, as we are discussing the example of the bicycle, whenever you are applying the brake, the amount of power you are applying through that brake depends how fast you want to stop your bicycle, right? You from your experience, if I apply this much amount of pressure or this much amount of force in the brake, I'm going to stop within this distance. That you can understand from your experience in bicycling. But what happens is, this distance or this amount of force keeps on changing depending on the track on which your bicycle is running, right? For example, if you are pedaling your bicycle through a very dusty road or a muddy road, depending on the conditions of the road, you have to change your policies. That's what we call optimization. So disturbances, these disturbances plays a very important role to manipulate the system. The system is being manipulated by us, but the demand of the manipulation of the system somewhere comes from the disturbances also. And finally, the target we want to achieve is here mentioned as a goal. So these are the very basic components of a control system, a conventional control system. Now, what we are going to do, I'm going to start with a very simple control system, an electrical control system, and from that, we are going to start understanding the complexities of much higher order systems. So let's take the example of a very simple thing, a spring mass dam shot system. It's a quite a usual example from the mechanical field, or you may consider the example of a RLC circuit, capacitor, inductor, and a resistor in a series, those sort of circuit. So what happens in those circuits are, first of all, you need to understand, we were discussing about this term, state vector. So what is a state vector? A state vector is nothing but it has entire information of the system dynamics. Okay, this is a mathematical representation, but the idea or the philosophy behind the state vector is it has all the information that's necessary to understand the dynamics of the system, first of all. So what happens is, how many state vectors should be present in a control system, or how do we define a state vector? The thing is that in a control system, all the components that has some sort of memory in that can be considered as a part of a state vector. For example, in case of a RLC circuit, the current through the inductor or the voltage across the capacitor at a particular time shows us how the system is going to behave with time. Right. So these parameters, the current through the inductor or the voltage across the capacitor, these can be treated as the state variable of a RLC series circuit. Similarly, in case of a spring mass dam shot system, the positions and the velocities of those mechanical systems, of the individual elements rather, will be considered as the state variable. So from this, what we can understand is a state variable is nothing but the reflection of the memory of the system. Okay, so that is what we call the state variable. Now, as we're discussing a very simple problem of an RLC circuit, in that, if a very simplest RLC circuit, if we consider one single resistance, one single capacitance, and one single inductance, in that you will find you are going to have two state variables. One is the capacitor, is the current across the inductor, and second is the voltage across the capacitor. Okay, now if the number of RLC components increases, then the number of states also gets increased, right? So the more the number of state variables are present in the system, the more complicated the system becomes. That is the basic idea behind this, all these conversations. So let's go to the real life examples. Systems are not limited to this RLC circuit or a spring mass dam shot system. These are very basic systems that we need to understand to get the idea of the bigger picture. So let's consider rather a larger system. For example, if we have to consider a grid network across a city or a village, whatever, an electrical grid network. In that case, we will find there are thousands, even millions of capacitance, inductances, or materials that behaves as capacitance or inductance present in that whole network. So the number of state variable increases simultaneously. So in this equation, x dot equal to fx comma u, in this, the order of the x will be of thousands, even millions. This is for the case of a simple grid system of a city. Now, if we keep on increasing the complexity of the system, let's try to understand the current situation, the COVID situation right now. So if we have to understand how to tackle the COVID situation, how to tackle the COVID from, how to stop it from increasing in a higher rate, or how to actually isolate the areas of infection. So if we have to do these kind of things, by the way, this is called epidemiology as a term. So in those cases, if you consider population of a particular place, then the health situation of every individual human being will be representing the state variable fx here. So that means if I am trying to consider a population of a small city, which is around, in India's perspective, maybe 10 lakhs, a very small city I'm considering, in that case, there will be 10 lakh individual state variable in the system. And that means, and one thing I must like to add here, this fx, this x is, if the system is a nth order system, this x, this matrix is of order n cross n. So the example that we are discussing, if there are 5 million people, or 5 lakh people in a particular locality, then the total size of this X matrix becomes 5 lakhs cross 5 lakhs. So you have to understand the amount of complexity, the amount of computing power that we need to actually process these sort of a system. This is the, as we are going in the real life scenario, these things that we need to consider very meticulously before diving into the real problem. Okay. Similarly, for example, if you have to consider, these were the cases. First of all, there are two types of very distinct cases we have. First of all, one are the cases where the system is a very complex system, but we already know the governing dynamics of the system. There are systems like that, right? For example, in case of a control system, a limit cycle or whatever, which is previously defined, or in case of a smart grid, the equations of the currents, electricities, voltages, everything is predefined. They may be very, very, very much complex, they may be very much non-linear, but they are all predefined. But in case of this epidemiology example, or in case of our brain, say, what happens if we want to model our brain? We don't know, we don't have any sort of a equation to model that thing. And even if we have an equation like that, I doubt how much computing power is it going to take to just manipulate those systems. Similar kind of things happen in case of weather prediction, or market regulation, stock market regulation. In these cases, there are innumerable parameters are present there, which are, each of the single parameter maybe are affecting the system in a very bizarre way, which we don't know, as we don't have a simple model of the system. So in those cases, conventional control systems has some sort of a what should I say, limitation in those problems. So continuing with that, the challenges of the conventional control system, as we have already discussed, first one is something called the non-linearity of the system. That means the things that does not abide by the laws of superposition. In those cases, calculating final values, or calculating the behavior of the systems, become much, much complex. Secondly, the unknown dynamics, that case that we have already discussed, that the case of our brain, where the system equations are not at all known to us. Third case is high dimensionality. What is high dimensionality? In case of for example, if we have a weather study, in which we are trying to formulate or model the weather of this earth, how are you going to do that? What do you have to do? We have to create maybe very small grids around the earth, right? Very small grid of maybe 1 square kilometer, 5 square kilometer, whatever you prefer. And that whole grid has to be covered throughout the earth. And we have to consider each parameter of our environment of that particular grid as a system variable or a state variable. That means the number of state variables will be innumerable because there are infinite, there will be a huge number of grids which are going to cover the whole earth. So that means the total system, the dimension, what is the dimension of a system? The system dimension basically is nothing but the number of parameters, the number of variable it depends on. Okay, so that means the high dimensionality of the system is also posing a very huge amount of challenge in the way of conventional control systems. And finally, the limited measurement. So if we have such a vast set of data to deal with, or to such a vast amount of area to control, then where exactly I have, for example, you have to understand the resources that we have as human beings are limited. For example, if we have to tackle the pandemic, then what we have to do? We have to do more vaccination. But the portion, the nodes at which we can vaccinate, those are very limited. For example, we can have only 1 or 2 vaccination centers in a very remote village. So that means we cannot have control or measurement of the entire system. That's why these limited measurement and limited control pose a serious threat when it comes to the point of conventional control systems. So from this particular perspective, a new approach has been introduced that is called the data-driven control. So what is data-driven control? Data-driven control is nothing but previously what we were trying to do, we were trying to formulate the system from a very mathematical perspective. We were trying to learn the laws that were governing the system. We were writing those laws. We were manipulating those laws. And then we are getting some sort of a control mechanism to manipulate the system. But in most of the cases, when we don't have any sort of identification, even we don't have any sort of identification of the system is completely unknown and it's very complex. In those cases, we cannot apply this sort of an approach. The case we are discussing, our brain. In a case of our brain, if you have to model our brain, writing an equation is next to impossible for that till now, from the knowledge that we have till now. So from these kind of shortcomings, this new field, data-driven control, is giving us some very good perspectives in this research area. So what is this doing? Basically, data-driven control is based on the amount of data that we are getting. So now in these days of supercomputers, very fast computers, highly efficient algorithms and stuff, what we are getting right now at every moment of time, each and every individual human being, we are generating huge amount of data. For example, the online shopping that you do, or the place that you travel, and the hotel you book via your app, in each of these cases you are providing your phone number, your mail ID, your name, your preferences, your vehicle preferences, a lot of amount of data. So as control system engineers, it was our perspective that rather than trying to formulating the system by the mathematical equations, we can do the complete reverse approach. What is that? We are having this huge amount of data, and by using the machine learning algorithms, which are nothing but these are non-linear optimization approaches, which are exactly a very good match of our systems, because as you can remember, we are dealing with non-linear systems with very huge amount of data. and also the very higher dimensional data. So in those cases, machine learning algorithms can actually understand the undermining trend that is happening in the data. Okay, so that's why this machine learning data driven control approach has been taken. So the very basic three approaches that are the field of study or field of research right now. First of all is data driven models, the one that we have already discussed. In this, what we do, we don't have a system which whose model or the governing equations are known to us. In those cases, we apply the machine learning algorithms to understand maybe an approximate level. It cannot be exact, but maybe a very near approximate level of the system. Okay, now in these approaches, the problem is that how first of all, you need to understand how we actually uh, use the control system approach. So what do we do? We, for example, if we have a particular nonlinear problem, what do? We first calculate the equilibrium points in that particular system. What is an equilibrium point? An equilibrium point is where the changes of the system are zero. So the system is not changing at those points. Those are very static points. So what do? We first identify these equilibrium points, and what we do is we try to understand the dynamics of the system around that point, right? Around that particular linearized point. So in those cases, the main problem with the huge amount of data is that we cannot keep on linearizing these millions or billions of state variables. That's an impossible task to do. So rather than doing this the first approach, first understanding the system model, then applying some sort of control mechanism, and the problem with those control mechanisms are they're very much what should I say? They're very much specific to systems. For example, if a control mechanism is working very fine or perfectly well in a particular system, it does not guarantee that it's going to work in a other system, or it does not even guarantee that it's going to act in the same system with the same precision after some amount of time, because it's a dynamical system. We cannot guarantee anything over here. So rather than modeling the system and after that applying some kind of linearized control method, for example LQR or anything robust control, what we should do is we actually derive the control strategy based on machine learning. It's something very similar the way we have learned anything in our childhood. This is the way the toddlers learn, right? They directly apply control strategies based on the data they have. For example, if a toddler is walking down a staircase, what is going to happen? First of all, if you have seen, maybe he once upon a time, this toddler, he tries to get down from that particular staircase, and without without any support of the railing or anything, he or she falls. So from this point, this particular toddler acquired this amount of data that if you have to get down from a staircase, it's better to have a support, right? So from the very next time when this same toddler gets down through the staircase, he does not apply that previous control strategy. He applies the new control strategy, which is nothing but he puts his hand on the railing, makes his balance perfectly well, then gets down to the next step. Okay, so this is the strategy for data driven control strategy. And third, the very most in fact the most complicated problems of among these all is the sensor or actuator placement, the case that we're discussing. We have limited amount of sensors and actuators, but technically we have unlimited amount of parameters that we need to control. So the position where exactly we have to put the sensors, or where exactly we have to put the actuators, so to gain a better control over the system, a better manipulation over the system, that is a very difficult topic from like 300-400 years. But now with the application of nonlinear machine learning algorithms, what we can achieve is, with this amount of data, the machine learning algorithm itself can actually figure out very well optimized positions by which, applying the least amount of resources, we can get the most amount of work out of it. That's it. So these are the three fundamental approaches that has been taken in the field of data driven control. Okay, so my topic is Cindy, that is nothing but sparse identification of nonlinear dynamical systems from data. I'm coming to that, but before going that, let's my final discussion on this small topic. This is called sparsity. So what is the sparsity of a system or a matrix? So in cases when you try to solve problems, all of you will see that in a lot of cases in electrical networks, on computer networks, whenever you try to apply matrix manipulations, you see a lot of matrices where most of the element or a huge number of elements of the matrices are empty. So what is the significance of this? What is the significance of a huge size, a huge matrix having 70-80% zero values or blank values? The significance is that by using very small amount of data, those non-null or non-zero data, we can actually represent a much larger system. For example, if you have a system which is being represented by a 10,000 cross 10,000 matrix, a basis matrix, for example, like this, that a DFT is a universal basis matrix. So for example, if we have a matrix like that which has 10,000 cross 10,000 values, so in those cases, if 80 or 90% of those elements are sparse, then as you can understand, only 10% of the element we need to store to get the whole idea of the system. Because what we know is all the other elements are already zero. We don't need to employ our costly memory space to store zeros. So that's why sparsity is a very important thing, or it's kind of a boon in case of engineers or scientists. So this is the sparsity of a universal basis. Universal basis means, okay, let's go to tailored basis, then we'll come to universal basis once again. So the case we're discussing, in that case, we were considering a basis function which has maybe 10,000 cross 10,000 parameters, right? The A matrix or the system matrix. So that means what? The system is of order 10,000 maybe in this case. So among those 10,000 matrices, one thing it's very significant is that by tweaking a very few amount of parameters among those 10,000 parameters, the system can actually be controlled or manipulated. I'm repeating my statement. Though these complex matrices form, they form huge size, huge, big, gigantic sizes of matrices, but among those variables, there are only, it can be calculated by various approaches, that there are very small number of basis functions, or small number of parameters. By tweaking or manipulating those parameters, you can actually manipulate the system. For example, let's take an example of a car. We have various elements in a car, various elements, huge number of elements. But if we have to consider the dynamics of the system, what are the main parameters that affect the dynamics of the system, of the dynamic of the car? That should be, one is a gear shifting, or second is the gas pedal, or the accelerator, third is the steering, and yeah, these are more or less the controls that are necessary for this car's dynamics. Yeah, you may have a very great sound system, you may have a very good airbag system, all of these, but these things have some other duties to do inside the car, which is not related to the dynamics of the car or the movement of the car. The dynamics that are necessary, that we have our focus on, that is the movement of the car. These parameters has nothing to do with the movement of the car. So though a car, if we have to define the state space of a car, though it will be having like humongous amount of parameters, but if you have to manipulate the dynamics of the car, it's enough by manipulating just 4 or 5 parameters to control this whole thing. That's why this tailored basis, the same example is true for this tailored basis that we were discussing. So universal basis consists of all the parameters that are actually present in the system, whereas tailored basis is nothing but it's a much reduced order system. That means it's, in this case we are having much less number of parameters. By tweaking those, we can actually change or manipulate the system. So from this perspective, sparsity has a very important role to play in case of both of these, universal as well as tailored basis functions. Because in case of tailored basis or universal basis, if we have majorly a sparse matrix, 80%, 70%, or 90% sparse matrix, then the amount of storage that is necessary as well as very much costly nowadays, that is getting reduced hugely, right? So for example, if there is a 90% sparse matrix, we need only 10% of the data that is necessary to store this matrix in case of a non-sparse matrix, right? In case of a non-sparse matrix, if we need X amount of data, and if the equivalent sparse matrix is maybe 90% sparse, then the amount of compression can be achieved is 90%. Only 10% data is necessary to compress the whole information, but not losing a slightest of bit of this. Okay, so that is where sparsity comes into play on this big picture. Okay, so without further ado, let's jump into our original topic, the deep learning of dynamics and coordinates with Cindy autoencoders. Okay, so what are those
Professor
Cindy
Prabrit,
auto?
Professor
Yes, sir.
Prabrit,
Yes, sir.
sorry
Yes,
to
sir.
disturb you.
Yes, sir.
It's 5:23 already. So if you
Yes, sir.
have a lot of slides left or many
Yes, sir.
slides left, then we can continue on another day. No problems with that.
So
Like how
what I
many
could
slides
do
more?
is I can simply show you the original work that Professor Steve Brunton has done, the coding
Okay.
portion. That will be very interesting for you.
Okay.
So
So
I'm just
if you think
jumping
it is
toward that portion
manageable,
directly.
if you think it is
Yeah,
manageable
yeah,
today,
yes, sir.
we can continue. Otherwise, we can continue on some other days. Okay.
Oh, sir, shall I stop it right now? Then I can continue it in
No,
a next
no,
day
no,
if you
no.
want.
If you can wrap it up in coming 10 to 12 minutes, no problems with that.
Yeah, yeah,
Okay.
yes, sir. Yes,
Go
sir.
go
Coming
ahead.
10 minutes, it
Go
will be
ahead.
okay, sir. Thank you, sir.
Okay.
Thank you,
Thank
sir.
you.
Okay. So let's directly jump into the system, what it actually is doing, the coding part. So in this case, you can see this is a diagram of a Lorentz attractor. These are the equations that are the governing equations of this Lorentz attractor. Now, this Lorentz attractor, we are trying to fit a Cindy autoencoder by which these equations, we know these equations, but if we don't know these equations and we try to formulate these equations from the data, that is the portion where Cindy comes into play. What we are going to do, these x1 dot, x2 dot, x3 dot, these three are being written as vector components in this x dot variable. See this vector, and what we are doing, we are creating the basis functions, non-linear basis functions. Actually, Cindy is creating a non-linear basis functions. As you can see, these are random basis functions. x1, x2, x3, x1 square, x1, x2. And after that, what it is doing, let me go to directly that. Yes, what it is actually doing, it is fitting the values that we are providing, the data that we are providing to this, to these sort of a model, and trying to calculate the original model. And by doing so, try to doing so, this is the discovered model that Cindy has achieved. So if you just try to compare these two, you will see that these two equations are nearly very same or similar to each other. And if you just tweak a few values, you can actually achieve the same sort of behavior, though these two has a slightly dissimilar kind of a behavior, these two. But if you tweak a few parameters, we can actually achieve the original Lorentz attractor model. So this is the success of Cindy. So how Cindy is working, let's just show me the code in a few minutes. So it's based on, there is a very great library they have designed. It's called PyCindy. It's available in the GitHub. I'm sharing all the links necessary for this along with this. So what they're doing is, in this library, what we are doing, they are trying to, this is a particular path that a system has to follow. And it has to follow this path on its own. There is no governing equation or nothing that has been told to the system. So by using the same method, this sparse identification method, by which they are identifying the coefficients of these nonlinear elements, what they are doing, first of all, they are creating a matrix, the basis function matrix, and then they're creating coefficients of those basis functions. See, if I'm just trying to zoom this in, if you could see this, see, these are the coefficients written in blue, green, and orange. These are the coefficients of the sparse matrix that has been calculated by the Cindy program itself. Just a second. Yeah. So this is the success of Cindy till now. And this Cindy has been applied to various complicated problems. For example, this Lorentz attractor problem, also a nonlinear pendulum problem. In both the cases, as they have shown in their publications, it has achieved considerable amount of precision and accuracy. For example, in case of the pendulum, this is the equation that the Cindy has discovered. As you can see, this is quite a precise equation for a pendulum. Okay, so that's what all about. Up to this was the topic that I wanted to discuss, and this is the last page I want all of you to see. This is the image of Professor Steve L. Brunton from the University of Washington. He's doing this wonderful work in this particular domain. I'm sharing all these resources along with you. If you are interested in this, just you can simply Google his name, all the resources, and he runs an exceptionally good YouTube channel on control system and database control. So if you're interested, you can just hop in. Thank you, sir. Thank you for providing me such a great opportunity. I want to finish it right now, sir, on this note, sir.
Thank you, Professor Prabrit. It was a nice lecture, as is also available from the comments in the question box. It could have, like, you could have continued with the whole thing. So
Sir,
maybe
it's
you
a
take
bit
up
lengthy.
some other day. Maybe you can take up some other
Definitely,
day and continue with the
definitely.
presentation from exactly the point I interrupted you. From there,
Okay.
you may kindly take over and continue with this presentation. I'm sure people will enjoy it because the comments in the question box suggest that way only. Like, I will read out some one or two comments, like Orijita Das madam started at 5:03 p.m. right away by writing wonderfully delivered lecture. Shamsundar Kaur sir complimented by saying a recommendable efficiency of presentation for audience, modulation of sound, clear volume and time gap of uttering. Okay, very interesting perspective by Dr. Shomik Gangopadhyay. So these are some of the comments which indicate that okay, it is good. Now there is one question. Before I
So,
take that question, I will request the members from IEM and UEM family to kindly answer the poll. So I have just launched the poll. and expecting the answer from your side to come within coming 1 minute.
Sir.
So it's around 17 or 18 seconds. So I will wait for 1 minute. We have already reached 42% of the polls or voting. I will request all members to vote at your earliest. So it's quite an even sort of voting that is going on. I will request all members to vote at your earliest. It's already 41 seconds, 42 seconds. We have reached 55% votes, quite faster than other days. But then it stops at 55%, which has also happened today. So I request all members to kindly cast your vote at your earliest. Okay, so it's 1 minute. I close it with 58% votes, which is a good number as compared to other days. I share the results and you will find it is, apart from the first answer, which is 51%, who says it has application in your field. The rest is quite even, 18%, 16% and 15%. 18% says they are not familiar with the topic. 16% says they are familiar with the topic. It doesn't have an application in your field, 15%, and 51% has application in your field. But one thing I will point out, Professor Prabrit, is that two answers would have been possible today. Like it maybe somebody is familiar with the topic and has application in his field, and maybe not familiar with the topic and has application in his field, not familiar and has an application in the field, possible, doesn't have application. So two answers, one out of A and B and one out of C and D was possible today. But still, it was quite a good number of votes today, and it is quite obvious that the people enjoyed your presentation. Any comments from your side on the answers of the poll, firstly?
Sir, thank you, sir. Thank you. This was a big encouragement to listen from all my senior and fellow colleagues and scholars. That's a great encouragement, sir. That's all I wanted
Okay,
to say.
so I will read out the only question maybe till now, like Professor Vishwadeep Basu Mallik has also written excellent lecture. Thank you. So Professor Amit Kumar Mondal has come out with the question, what is the difference between static and equilibrium points?
So there is static and equilibrium point. So an equilibrium point is a point where there is no change is happening in the system. So x dot, any change is equal to 0. Static means basically the same, sir. There may be some shades of changes that I am not familiar with, but in basically whenever we deal with control system, these sort of things we deal with, we name them as equilibrium points, and as well as a non-dynamic system which is not changing with time. In those cases we call these as static systems. So
Like in
basically
terms of a layman, static is something like which has not started yet. Maybe if you're talking about a
yes, sir.
vibration, static is something which it has not started yet, or maybe
Started, yes,
something
yes,
like
sir.
that. And equilibrium is
Yes, sir.
something where it reaches that static point somewhere
Yes, sir.
possible.
Yes, sir. Yes, sir. Yes, sir. Definitely, sir.
Maybe that way it can be,
Definitely,
like
sir.
from a
Yes, sir.
layman
Yes, sir.
point of view.
Definitely.
Okay.
Yes, sir.
Okay,
That's
so
a great addition, sir.
thank you, Professor Prabri. There are many comments on the question box from Professor Amit Kumar Mondal, Shoikat Chakraborty, Aditya Roy, Indranil Basu, senior professors like Professor Indranil Basu, Dr. Subroto Chattopadhyay, senior professors have said very relevant topic and excellent session. So that's
Thank you, sir.
a good point for you, good situation for
Thank
you.
you, sir.
Thank you, Professor Prabrit, and thanks to all IEM and UEM family members. Thank you.
And one more thing, sir, for just the last thing, I am just going to share this PPT with anyone who is in charge over these sort of things. Anyone who wants to have a look in this PPT can have access to that.
Yes, you can kindly post it in the UEM Jaipur board, discussion board.
Definitely, sir.
I will
Definitely,
forward
sir.
from there.
Definitely,
I will
sir.
forward. Okay.
Definitely, sir.
Thank you.
Definitely.
Thank you.
Thank
Thank you.
you, sir. Thank you.
Thank you.
Okay. Good night, sir.